Welcome to lecture 25. In the last class, we were looking at the methods of determining shear strength of soils. And the first method we looked at was direct shear. Hi. So let's look at the methods of determining shear strength of soil. And we were looking at what is called as a direct shear test or shear box test, wherein we have one soil sample is contained in two boxes, wherein the plane of shear is defined. You are shearing along. So we apply a normal stress, sigma, and we apply a shear force T so that the soil gets sheared along this plane. We also use a dial gauge to measure the vertical displacements, and we use another dial gauge to measure the horizontal displacements, so that you can plot delta horizontal versus T, and usually we get a curve of this kind or another curve of this kind. This is for loose sands and this is for dense. Then we can, if it is a clear peak, we take it as T max, and if it is asymptotic, we take at a relatively large displacement. Then you can calculate the maximum shear stress as equal to T max by the area of the shear box. Area generally is 6 centimeters by 6 centimeters. So you will get the maximum shear stress corresponding to one normal stress. And then you can plot normal stress with the shear stress, and you will get 2, 3, 4 points, and you join them, and you will get the Coulomb, or shall we say more Coulomb failure criterion, according to which the intercept on the y-axis is called C cohesion, and the slope or the inclination of the failure envelope is the angle of shearing resistance. C is called cohesion, and phi, technically and more precisely, we should call it as angle of shearing resistance. People call it loosely and without realizing that it is a friction angle. They use the word friction angle, which is not really correct, because the resistance is to shear and it is more than friction that matters. The reason is, if I look at it now, this graph, if you see, and we are saying T, and if I plot delta H versus the vertical dial gauge reading, if you remember, we put it on the soil, another dial gauge here, this is delta V, and you will see that either the volume goes down or goes up. This is negative and this is positive. So during shear, we do the soil sample does some extra work, and the resistance is due to friction plus work done for volume change. So it is more precise to call it as angle of shearing resistance. The direct shear test is a very simple test. We can do it on sands particularly, because, and most of the time we do it on compacted samples prepared in the laboratory. The advantages are, it's very simple and can be done on particularly granular material like sands, specifically sands, and on samples compacted in the lab. The disadvantages are, the disadvantage of direct shear test are drainage is not controlled. So during the test, if it is a saturated or even partially saturated sample, certain amount of water may escape. And there is no way we can control the flow. It will happen by itself and we cannot control it. Second is actually also difficult to do test undisturbed samples. You may like to test a sample taken from the ground. Usually we take it in a sampling tube, and you cannot get easily a block sample 6 centimeters by 6 centimeters by 2 centimeters. That is the usual size. So it is very difficult to do this. The third is the failure plane is predetermined. We have no control on the failure surface because you are shearing along this plane. This is AB, and the shearing takes place right along the surface. But in real soil, it may be any plane other than the predetermined one. Because of this, we need to go for a more sophisticated testing, and which consists of taking samples in a cylindrical form and testing in what is called a triaxial apparatus. So what we do normally is we can take a cylindrical sample, usually 1.5 inches diameter by 3 inches length. That is, say 37.5 millimeters by 75 millimeters length. These are easy because I can take a sample from the field in a tube. This is an undisturbed sample. And if I look at the surface, usually this sample diameter is 100 to 150 mm. So what we try to do would be to drive 3 smaller tubes inside, each of them obviously 37.5 millimeters, and then I can get a nice relatively undisturbed sample which is cylindrical in shape. This diameter is 37.5 and length is 75 millimeters. And in the standard, what we call, I think you should be familiar from now onwards, what is called as triaxial testing. This is the most common and desired testing for soils, especially for fine grain. That means silts, clays, silty clays, sandy clays, silty clays, silty sands or sandy silts, etc. Basically, where the fines content is usually more than 20 to 30%, then when you take a sample, it will stand by itself. You cannot have a sample of pure granular material. If I try to take it, a sample like this, the sand gravel will fall down, so you cannot usually get a cylindrical sample. But if you have a fine grained soil, you can get a sample. What we do here is first put a latex membrane. So let me draw the schematic. we take the sample 37 by 75, put a filter paper like in the odometer test. Then we put a porous stone. And then we provide a latex, or you can say rubber membrane. So that it will not allow water to either escape out, or it will not allow water to come in. So if water tries to go out, it's stopped, or you cannot expect water to go inside. The whole idea is to insulate the sample from outside influences, and you can control drainage. On top of it, you provide a loading platen, and you assemble this on a pedestal, which is contained, here is a base, and then I have a cylindrical chamber. This is the cylindrical chamber. So you have the sample in the center, and all around is a chamber in which I can control or apply water pressure. We provide some rubber O-rings so that there will be no leakage on any of these sides. So the whole sample is contained by the latex membrane. So you have the sample here, filter paper, porous stone on the bottom, a filter paper, porous stone on the top. This is called the loading plate. And the loading plate is connected to a piston, and the whole thing is in a loading frame. So here, this goes with a proving ring here, and this assembly is on a platform, and you have a motor which keeps rotating and lifts the base plate. So the whole sample is lifted and it is pushed against this upper bar so that you get a reaction. So you have a rigid bar and you are pushing it from the bottom, so you get vertical stress applied. What we do here is we have a connection from which I can apply water pressure. All this is filled with a fluid. This chamber, we said, which encloses the sample with the latex membrane, is filled with water. And then you can apply a pump and then increase the pressure. Then we also have a connection from the bottom of the porous stone, which we connect. You have a valve here. I can connect it to a burette, any volume measuring device, or a pore pressure device. I can connect it to, let us say, or I can also take another connection and a pressure measuring device. Shall we say simply pressure gauge? So please remember, it's a very simple one, but involves a certain amount of experimentation. We take a sample, we contain it in a rubber membrane. It will separate out the water outside from entering into the sample. The rubber membrane also prevents water escaping from the sample into the chamber through the sides. If there is any water that has to escape, it has to go down only through the porous stone at the base. So we provide the filter paper, porous stone, and put the whole assembly on the pedestal here. And on the top, the filter paper, porous stone, and then you have a loading platen. The loading platen is connected to a piston. The piston goes through the chamber, and then it, through a proving ring, is taking reaction from the top reaction frame. So that if the whole assembly is being lifted at a constant rate, so the load is applied, or loading is through constant rate of strain, which means when the motor is running at a constant speed through a bevel gear, we convert rotation into vertical displacement so that it keeps moving vertically at the rate of, let us say, something like 0.1 millimeter per hour or per minute or whatever. You can adjust the speed from very, very slow to very fast speed. So what you find here is that the soil sample is loaded by lifting the sample, taking reaction from the top platen. And the sample is confined with a fluid pressure, and this is to simulate what happens in the ground. If you remember, in one of the earlier classes, we said the state of stress inside the ground, if I take a sample here, the sample is subjected to sigma V and sigma H, and of course U, or shall we say initial values, so that you have the sample subjected to a confining pressure. You would like to simulate that condition in the laboratory so that the sample is identically loaded as it exists in the ground. So once you put the assembly here and start loading, there are two options. If I open the valve here, the water may escape and then it will get collected in the burette, so that when the water is coming out, I can find out how much water is coming out. So the volume of water that escapes can be measured, and you know how much volume change is taking place. This is very similar to the odometer test, in which the water escapes, and instead of measuring the volume of sample, volume of water coming out, I can measure simply the settlement, because the volume change is proportional to, or volumetric strain is proportional to the axial strain. If you remember, we said that S by H, settlement by, is the vertical strain is equal to volumetric strain is equal to delta V by V naught. So there in the odometer, I don't have to measure delta V, I measure the settlement S. And then if I know the thickness, initial thickness, as also initial void ratio, we could calculate the change in void ratio, which is effectively change in volume. The soil grains will never compress. Any volume change we get is because of volume of change in volume of voids. In the triaxial apparatus, we also measure the vertical displacement, but we also measure the volume change. So the two measurements are, now that you are familiar with the scheme of testing, please note that you have a cylindrical sample with latex membrane, and all-round pressure applied this by the fluid pressure, vertical load is applied by the reaction frame. And the bottom of the sample is connected through the porous stone. The filter paper prevents the soil samples coming out. The porous stone is to collect the water connected to this tube. And you can measure either the volume change, or if you close the valve, I can measure how much is the pore pressure inside. And please here, we try to also make sure that the friction here is very small, so that the sample will have least amount of friction. Even if it is there, if you have L by D equal to 2, that means the length to diameter of the sample is 2, at least the center is not affected by any friction on the top and bottom faces. Let us now look at the schematic of the same. So what you have seen is the apparatus and the testing procedure. What we have is a sample, whatever with the latex membrane you have. This is sigma 3, called the hydrostatic pressure, or shall we say equal all round pressure. Because when you apply the water pressure, it not only acts from the sides, it also will act on the top of the sample. So you will have sigma 3 all around. Now when I start the motor and lift this sample up to take reaction from the top, what you then will have an additional vertical stress. We call it as sigma 1 minus sigma 3, which is called the deviatoric stress. The vertical stress that we apply is over and above the hydrostatic pressure the sample already has experienced. So this is the sample which is subjected to an equal all-round pressure, sigma 3, which acts all around the sample and on the top, plus the vertical reaction force gets converted into the deviatoric stress. We call it as the difference between the major principal stress and the equal all-round pressure. If I combine the two, what you will get is the simple situation. Again, let me show you. Sigma 3 plus is equal to a lateral confining stress sigma 3 and a vertical stress sigma 1. Now you get an idea. We can go for the more Coulomb kind of stress state, wherein I have the minor principal stress, which is equal to the confining pressure sigma 3 and the major principal stress sigma 1. So what we do in the test procedure is in two stages. Test procedure, like in shear box, we had first normal stress applied and the shear stress applied later. Here we apply first all round pressure sigma 3 applied first, and then we apply the deviatoric stress sigma 1 minus sigma 3. When you apply these stresses, you have a choice of controlling escape of water or sealing so that there is no water escape. So outlet, I can measure delta V or I can measure delta U. So the combined effect will be delta V, say delta V1, delta V2, total is equal to delta V1 plus delta V2, or you can have 4 pressures. So basically you have a cylindrical sample which is loaded in 2 steps. First we apply the all-round pressure. After the soil gets stabilized, we apply the deviatoric stress. Why we call it deviatoric? Because it is over and above the hydrostatic stress. But once you add sigma 3 with the deviatoric stress, you will get sigma 1 and sigma 3 as the 2 major principal stresses that we can have in this testing sequence. Now, the simplest form is that if you do not apply sigma 3, if sigma 3 is equal to 0, no lateral or confining pressure. We call it as unconfined compression test. Usually we do it on saturated fine-grained soil. And we do not measure anything other than the deviatoric stress. So you apply sigma 1. Please remember sigma 3 is 0. So sigma 1 minus sigma 3 is equal to, if sigma 3 is equal to 0. And then you measure the vertical strain. How do I get vertical strain? You are going to put a dial gauge on top. So you will have some delta. And you know the length of the sample. So the vertical strain is equal to delta by L. If you put a dial gauge on the top, as soon as you know the mesh displacement, divide the displacement by the initial length of the sample, which is equal to 75 millimeters plus or minus 0.1, 0.5 millimeter, I can get the strain. And you will find that the stress strain curve looks something like this, in which case I take it as sigma max, or shall we say this is equal to sigma F failure. Please remember, strength is defined as the maximum stress a sample can carry. Definition of strength is, of any material, the maximum stress a sample can withstand. So you can see that whatever you do, you may increase the deformation, but the stress it can carry is limited by this. So what you have found out is the vertical stress the sample can carry. So what we have for a unconfined compression test, you have sigma 1 maximum at failure. We said sigma 3 is 0. When you say unconfined, it means sigma 3 is 0. Now if you plot sigma versus tau in the mode circle, sigma 3 is 0 and sigma 1 is maximum. You get a mode circle. One end is passing through the origin, the other end is given by the unconfined compressive strength. So sigma 1 max is called unconfined. If you get this mode circle, we try to make a very simple assumption and say the more envelope or more column envelope is tangent but in a horizontal direction. Then you will get the maximum shear stress, tau max, will be equal to half of the diameter of the mode circle. So that will be equal to sigma 1 max by 2. So you can say that the maximum shear stress the sample can carry is equal to half of the maximum unconfined compressive strength. This line is horizontal, so phi is 0, and what you get is the C, which is, we are not allowing any drainage, so this is the cohesion, or shall we say cohesive strength of the sample, which is equal to half of unconfined compressive strength. You do the test in a fairly short time, within maybe less than an hour, probably half an hour to 40 minutes. So there is no time for water to escape, because fine-grained soils permeability is very low. Even to travel a distance of something like 10 or 20 mm, it would need more than a day or two. So during the test, water will not escape. So the soil is in a relatively undrained state. So we say undrained cohesion. I'll come back to that little later. Is equal to half the unconfined compressive strength. This is what is generally done as a routine test on the samples we collect from the field from different depths, so that I can plot and get some picture as far as the unconfined compressive strength or undrained strength of the sample by taking samples from different depths. This is the ground level. You take samples at 1, 3, 7, whatever this depth. You can plot Cu versus depth, and you may get something like a strength profile, how it varies with depth. This is a very simple way of characterizing the ground, and we do it rapidly. The only problem is this strength is not all universal. We need a more sophisticated one, for which we go for the triaxial testing, and there are 3 types of triaxial testing with sigma 3 obviously. So let's say we call it as triaxial. We have 3 types. One is called the drain test. Second is called consolidated undrained test, and third is the undrained test. You want to be a little more elaborate, you can say unconsolidated undrained test. Instead of saying twice, we simply say undrained test. There are 3 variations in this, the way the test is done. In the drain test,